Yeah, okay, so our next speaker is Abdenacer Makhlouf with an introduction to algebraic deformations.
Thank you. Hi, everybody. It's a big pleasure to give this lecture. And I don't know what is the rule. Maybe you have to talk 50 minutes or 55 minutes and keep five minutes for questions. Or of course, if you can interrupt me if you want to ask any question during my lecture. No problem for that. Huh? Okay. Yes. Then let me start by introduction to. Then the title is Introduction to Algebraic Deformations. Does that I mean by that? In fact, what I'm interested in is to deform algebraic, to talk about formal, more precisely about formal algebraic deformations of algebra structures, of algebraic structures. Huh? And more precisely, I will deal with one parameter formal deformations, and this was introduced by Gerstenhaber in 1964, more precisely. 1963 introduced some cohomology related to that, and then introduced this one parameter formal deformations for associative algebra. And this type of deformation was or were then extended to Lie algebra. Then this was for associative algebra, and by Nijhuis and Richardson. This was extended to Lie algebra. And this was based, in fact, on already earlier works about complex structures. Then this approach was based on works by Kodaira and Spencer about deformations of complex structures. And manifolds. Huh? Okay. And what are the ingredients of this this approach? What we need first, the object we would like to deform, and these are algebraic structures. This could be any non-associative algebra. I will come back to this later. This includes, of course, associative algebra. Lie algebra, and let's say I saw that Alberto Duque was talking about octonions, and these are alternative algebra. Etc. Huh? And of course, we can also deform other type of algebraic structures, like operators, or bialgebras. What are bialgebras? The bialgebras are algebra plus coalgebra with some some connection between both, with plus addition conditions, expressing compatibility. And this is the first ingredient I was talking about, and the second ingredient is formal power series. And what I was saying before is that we are doing one parameter formal deformation. This means that we use formal power series on one variable, t here, but of course we can also construct a theory using several variables t1, ts. And from this, we can extend k-linearity to kt linearity for our algebra, and we can also consider formal spaces. And the formal space, if you have k vector space, then you can extend it to formal space AT. And the main ingredient to control this deformation, these deformations will be cohomology. And in fact, the main result in Gerstenhaber works was to connect this topological or formal deformations using this formal power series to some invariants of the algebra, which are the cohomology. The main results express how to construct or how to control this deformation using the cohomology of the algebra. Of course, about cohomology, each type of algebra has its own cohomology. We can talk about Harshad cohomology for associative algebra. And this is for associative algebra. And Chevalier-Eilenberg cohomology, for example, for Lie algebra. This is for Lie. Okay, and this is the three ingredients we will play with during this week. Of course, I will come back to each of them and give more details and more information. And now maybe let me just give you some motivations. As usual, in algebra, we try to get some motivation from physics, and this is the case here. And in physics, what is the main concepts? We have two main concepts, which are states and observables. This is the two main concepts of physics, and usually we talk about classical mechanics. So maybe classical mechanics, and we have also quantum mechanics. Move to blue. And as I told you, what will be the state for in classical mechanics? State here will be just a point on a manifold, a point on a manifold. And And what about quantum mechanics? This will be a projective space of a Hilbert space. Projective space of a Hilbert space. Now, what about observables? And this is, let's call this manifold M. And this is a function for classical mechanics in C infinity M, which are maps from M to R. Then this, the set of these observables has a structure of commutative algebra. And what about observables in quantum mechanics? This is given by bounded operators, then by joint operators. Of H. This is the space we were dealing before. And here we have to consider all the bounded operators of the Hilbert space. Operators. Okay. And the values of an observable this is, of course, the image of point M. And here this is the spectral value of H. And now, what about the dynamics? Here we have the well-known Hamilton equation. And here we have the Schrödinger equation. This is the dynamics of states. And now about the dynamics of observables. And this is given by the following equation: df dt equals to the bracket fh, h being the Hamiltonian. And here it is given by the equation a h bar d of a dt ah. Okay, and this is a commutator. And now, what about the structure of observables? Then here, if I consider all the ingredients I mentioned already, then we have this set C infinity of M, which are functions M. We have the pointwise multiplications, which give a structure of algebra to C infinity M. And we have a bracket I mentioned already, and this triple is considered to be a Poisson algebra. In fact, C infinity M with the bracket, this is a Lie algebra. And C infinity M with the dot, this is an associative algebra. And we have a compatibility condition between these two operations. And for quantum mechanics, we have this set of bounded operators. Okay. H by the bounded operators H, and this carries a structure of non-commutative associative algebra. Okay. Then now, what is the relationship between the two mechanics? In fact, one can say that a quantum mechanics is somehow a deformation of classical mechanics. Huh? This is the relationship we can express and which give a link to the aim of our lectures. Huh? Okay, and of course this deformation, we have here a commutative. We have this operations, this operation here, dot, which is commutative, and in order to get something in quantum mechanics, we have to deform this multiplication in a way to get something non-commutative, and of course we have to take in account this Poisson bracket in a sense I will explain later. Huh? Okay, then some research says that we can see, and mainly a paper by Dijon School by Bayen, Flato, Lichnerowitz, and Sternheimer. Then they have this theory saying that a quantum mechanics, a quantum mechanics is a deformation of classical mechanics. And this is through a star product. And what is this star product? And this star product is, we start with this pointwise multiplication, and we get, if you have two functions, f and j, then we can deform this. This is f dot j plus t b1 fj plus t square b2 fj, etc. And the challenging question is how to construct such a deformation. Here, of course, B1, B2 are bilinear maps, and how they are related to this Poisson bracket. In fact, the Poisson bracket Fj this is 1/2 of B1 Fj minus B1 GF. Okay. Oh, sorry. This is the relationship between. Then, if you have, of course, this star product should be associative, satisfy the associativity condition, and the connection with this bracket is given by this first term of the deformation, which is B1 here. And the theory says also that this B1 is in fact a two-core cycle in the Hochschild cohomology. This is how to, and this is a general fact. Okay, then this is one motivation to study this deformation. And maybe very quickly, the other motivation, motivation 2, this is so-called quantum groups. In fact, we have the concept of group, which plays an important role in mathematics and physics. And now, if you deal with multiplications, what you need is, of course, if you dualize one important fact for groups, so one important property of the groups is that they are autodual. If you take the dual of the dual of a group, this is a group. Okay. Now, if I consider a multiplication, what is a multiplication? A multiplication is a map going from a vector space A, is a bilinear map, going from A tensor A or A times A in A to two elements xy. You associate an element mu xy. And of course, we can see this is a bilinear map, and we can see it as a linear map by considering tensor products. Then I can say that this mu now is just a linear map from A tensor A to A. Now, if I dualize this, then what I get is something going from A dual to A tensor A dual. Then mu star here is something going from A star to A tensor A star, the dual of this vector space. Okay. And of course, if we are in a good case, for example, if A is finite dimensional, if A is finite dimensional, then in this case, that what we have is a map, mu star, going from A tensor A into A tensor A star, sorry, tensor A star. Okay. Then this is an operation or a map going from the other side around with respect to the multiplication, and this is what we call a co-algebra. And now, if we want to get something, of course, if I dualize an algebra, I get a coalgebra. Then the idea is to construct a structure which is consisting of an algebra and a coalgebra with some compatibility condition, and this is what would lead to bialgebra and also to Hopf algebra. I will give a concrete definition in a moment. Hopf algebra. And then we can get something similar to group, to concept of groups. Then we get something which is called quantum group. And what is a quantum group? Quantum group, we can define it as just a non-commutative and non-co-commutative Hopf algebra. And the examples for this are enveloping algebra, which carry a natural structure of Hopf algebra. And the idea to get quantum groups is to deform this Hopf algebra of enveloping algebra. And these quantum groups are deformations somehow of Hopf algebra structure of enveloping algebra. Enveloping algebra. For of course for a given Lie algebra, and here what we consider usually they are simple simple Lie algebra, which usually cannot be deformed if they are regarded only as a Lie algebra, and their enveloping algebra cannot be deformed as well. But if we consider this Hopf algebra structure, we can construct some deformations that define what is called quantum groups. And of course, this is also related to physics, and what we have in quantum mechanics, we have the notion of integrable systems become very complicated, and Fadeev and his group developed a theory to study this the system, this integrable system by what is called scattering method. Sorry. Yeah, so it's a scattering method. Huh? Okay, now this is done by Fadeev and collaborators. In fact, it's inverse scattering method. Huh? And in fact, who were based in St. Petersburg, in Russia. Huh? In fact, all these concepts of Hopf, of algebra, by algebra started from the works done by this St. Petersburg school. Huh? Okay. Then this is a very general fact, and maybe just an introduction to what I would like to talk about. Now, if you allow me, I will come back to some basic things. I don't know how many students are following these lectures, and I don't know what about the level required for these lectures, and maybe it's better to start from scratch and discuss basic things. And if you know very well what I will talk now about all this algebraic structure, it doesn't matter. I'm so sorry for you. And but if you don't know, that's good. Huh? In order to be sure that everything is known, let me start by some basics about algebraic structures. And first of all, maybe the first structure we would like to study is the structure of algebra. Let me define what we mean by associative algebra. What is an associative algebra? We fix in these lectures, we fix K. We let K to be a field of characteristic 0. Just in order to make things easier, but of course the theory could be generalized to any characteristics, and also we can talk about algebra over rings in general. Now let A be a K vector space. Then what we call an associative algebra is is a pair of A is a pair A mu. Sorry. A is already fixed as K vector space, and mu, where mu is a bilinear map. Mu going from A transfer A times A to A, such that we have the two following condition. The first condition is the associativity, which means that mu of x, y, z, this should be equal to mu of x, mu, y, z. This is for all x, y, z in A. Okay, then this is the first condition, and we say that the algebra, the associative algebra, is unital. Sorry. Is unital if there exists an element for example, E in A, such that mu of EX, this is mu of XE, this is X for any X in A. Okay, and usually what we say that we have an algebra if it's an associative algebra, and which is unital as well. Okay, but in general, we can consider associative algebra to be just a bilinear map mu satisfying this first condition, which is the associativity condition. Now, if I told you that we can generalize this definition, if we have a commutative ring in general, we can let R to be a commutative ring. And an R algebra is a unitary R model A on which I'm sorry. We define a bilinear map A times A satisfying the associativity condition and the existence of the unit. Satisfying the associativity and the existence of the unit. It's denoted by 1A. Then we can remark that if we have this, then every R algebra is a unitary ring. Every R algebra is a unitary ring. And the bilinearity of the multiplication is equivalent to the right and left distributivity. And conversely, if A is a unitary ring, and a right R model, satisfying this condition, I mean this distributive this condition x y a equals x y a equals x a y for all x y in A and A in R, then A is an R algebra. A is an R algebra. Okay. Now, if we want to use what we call a Hopf algebra language, then in this case, an algebra is a triple A mu eta, where mu and eta are linear maps. Then mu is a map going from A tensor A, then here you have to use the tensor product A to X tensor Y, X or Y, we associate mu of X tensor Y. And eta, this is a map going from K to A. And to A, we associate A eta of A. And eta of A, since I am assuming that these two maps, mu and eta, are K-linear, then I can write this eta A, I can write it as A. This A is K, eta 1. And here you recover the usual unit, what I called before E. Here it is eta 1. And now the associativity, these two maps should satisfy satisfying the associativity which is expressed by and of course the existence of the unit which can be expressed by the following commuting diagram. And how I can write these two diagrams? Then I start with A tensor A, Then from here, you go with using mu tensor the identity, get to A tensor A. And again, here with mu, I get to A. And now from this side, you apply identity tensor mu. I get again to A tensor A. And then again, here I use mu. And this diagram should commute. And this expresses the associativity. Okay. And the unitality is expressed by the following diagram: K tensor A. I apply eta tensor identity here, get to A tensor A, and they can also apply identity tensor eta going from A tensor K from here. And here, if I apply mu, I get to A. And here I use the identification, because A is a K vector space. Then I can identify A tensor K to A, again here. This isomorphism. And then the commutativity of these two diagrams expresses the existence of the unit. Huh? Okay. What about examples? You know, lots of examples for sure. Of course, basically we have this Cn and Rn, which can be endowed with the structure of associative algebra, but by the usual multiplication. And we have the polynomial rings. Kx, this is and Kx1 xn. Huh? I assume that the polynomials are commutative here. Up to now, I have only commutative examples, and the first non-commutative example starts with is given by matrix algebra. M and K, square matrices of order n with coefficients in K. This is a non-commutative unital associative algebra. Now, if I start with groups, with a group, let G group G, we can construct here G is with elements, group G with elements alpha I. Then we can construct the vector space Kg generated by the basis E alpha I. And here we define a multiplication E alpha I, E alpha J. And this is E alpha I times alpha J. And here we are using the multiplication in the group. And here this is called the group algebra. Of course, the unit of your group gives E1 would be the unit of your algebra. You can also construct if you have two algebras, A and B, two algebra over K. Then one can construct the tensor product. The tensor product A tensor B is also a K algebra. I mean here, when I say algebra, I mean associative. And sometimes if we are working with non-associative algebra, when we say algebra is just a vector space with a multiplication without any restriction on the multiplication, okay? But here we're dealing with associative algebra, and allow me to talk about just algebra for saying associative algebra. And here the multiplication, if I take element U1 tensor V1 times, yes, any question? U2 times V2, then this is U1 dot A U2 tensor V1 dot B V2. Okay. Then we can construct by tensoring a lot of new algebra. One were to say that we have morphisms. Huh? And if we have now two algebra, let us use now this half algebra notation. Let A mu eta and A dash mu dash eta dash be two algebra. Then I would like to show that using this this morphism that the set or the class of all algebra forms a category. And what are the morphisms here? Linear map, F from A to A dash is an algebra morphism. If you have these two conditions, mu dash composed with F tensor F, this is equal to F composed with mu. And F composed with eta, this is eta dash. And of course, we have an isomorphism. If F is bijective. Okay. Then in this case, you can write mu to be F inverse composed with mu dash, composed with F tensor F, and eta, this is F inverse composed with eta dash. Okay. But maybe just to say a few words about coalgebra, then make it complete here. Then with this we can say that this the class of R algebra forms a category. Then we can talk about representations and models of algebra. But let me just maybe introduce coalgebra and this new type of algebraic structures. Then if I dualize what is a coalgebra, is a triple let's say also C delta epsilon, where C is a K vector space, delta, this is a map. Delta is a map going from C, sorry, not A, C into C tensor C, and eta going from A to K are linear maps. Maps satisfying. What do they satisfy? In fact, you get, we have algebra, from algebra we got co-algebra, then the associativity becomes co-associativity. And to get it, we have just to reverse the arrows, reverse the arrows here, and replace everywhere mu by delta. Then here what they get is delta tensor identity. Here a reverse and they get delta. Here delta. And here identity tensor delta. Yes, then here this is that what I get here is the co-associativity is delta tensor identity composed with delta should be equal to identity tensor delta composed with delta. Satisfying, then identity tensor delta composed with delta equals delta tensor identity composed with delta. And this is what we call co-associativity. And we get in the same way co-unitality by reversing the arrows here and replacing eta by epsilon. And this is epsilon tensor identity, and here this is delta, and here I have identity tensor epsilon, and I have this delta. And now what I have is delta epsilon tensor identity composed with delta equals identity. Epsilon tensor identity composed with delta, this is equals identity and should be identity tensor epsilon composed with delta. And this is the co-unitality. This is what we call a co-algebra. And now we have to gather together, to put together algebra and co-algebra to get what we call a bialgebra. Oops, sorry. Bialgebra. Now a bialgebra is a tuple. We have A, mu, eta, delta, and epsilon, where then we have this A, right? A mu eta is an algebra. A delta epsilon is a co-algebra. And here we have a compatibility condition, which can express as delta and epsilon are algebra morphisms with respect to mu. What does it mean? That is, delta composed with mu. This should be mu tensor mu composed with a flip tau composed with delta tensor delta. Okay. This is and what is tau here? Tau is tau tau of x1, tensor x2, tensor x3, tensor x4, then this is equal to x1, and I have to flip or swap this x2 and x3. Tensor x3, tensor x2, tensor x4. This is what tau. Huh? And epsilon composed with mu. This is epsilon if I apply it to of x, y, yeah, if I apply it to elements, it's a bit better, of x tensor y, this is epsilon of x, epsilon of y. Okay, then this is the compatibility condition. Of course, we can also have a compatibility condition about the units. Then for unit the delta 1, this should be 1 tensor 1, and epsilon of 1. Then this is 1 of A, A, 1 of A, and this is 1. Well, this is 1 of K. This is the I, 2, I, 3, and 4. This is the 4 condition expressing the fact that delta and epsilon are algebra morphism with respect to the multiplication and compatible with the units. Okay. We have 2 minutes left, and the next structure is a Hopf algebra. In fact, before this, one can show if you have an algebra and co-algebra, or maybe let's keep the same vector space. We have this remark or theorem. Now, if you have a bialgebra, let A be a bialgebra with the same ingredient as before. Now we can endow on and A, endomorphism of A or Hom A to A. We set that F tensor. We constructed a product, which we call a convolution product, and it endows F star J, and this is mu, tensor mu, composed with F tensor J, composed with delta. Okay. And this is the product constructed using the multiplication and the co-multiplication, and now if with this product and A with this star is an associative algebra. And its unit is eta composed with epsilon. Then this and A is a unital associative algebra where the unit is eta composed with epsilon. If now we say that an endomorphism S is an antipode, then we have a definition. An inverse of identity of the identity on A over on A is called, when it exists, because it doesn't exist all the time, when it exists, an antipode. And what is an antipode? Like an S is an antipode if we have S convolution with identity, with respect to the definition mentioned already, identity star S and equals eta composed with epsilon. This is the definition of an antipode. When a bialgebra has an antipode, we say that it is a Hopf algebra. When a bialgebra has an antipode, we say that it is a Hopf algebra. Just maybe if you within 3 seconds, I will give you an example and finish with this example. If you remember, we constructed KG, a group algebra. For this group algebra, we mentioned the multiplication before. Now I have just to construct the co-multiplication, delta of E alpha, E alpha I. This is, and then this is E alpha I tensor E alpha I. We say that this element is a group-like element, is it correct? And eta of not eta but epsilon of E alpha I. This is always 1. Okay. And S of E alpha I. This is alpha I inverse. And this KG is a Hopf algebra. This is an example of Hopf algebra. Okay. Maybe I should stop here. Time is over. And your questions are welcome. Thank you.
Okay, let's thank the speaker. Are there any questions, comments?
Sorry, but cannot hear. I didn't hear the question. If there's any question.
So is there any question?
Hello.
Hello.
Can you hear me?
Oh yes.
Yes, we can hear you.
Okay. Thank you for the nice talk. I was a bit confused with your example when you give the example that you gave just after the definition of the Hopf algebra. When you say Cn and Rn are algebra, I'm still wondering how one can make the product of elements.
You mean for this example, the product is just I times E alpha j. This is E alpha I alpha j, and here we are using the multiplication in the group. This is the product.
No, I mean I'm talking about the Cn and Rn, not the group algebra.
Okay. Yeah, but the product is just a multiplication, usual multiplication. I mean, how to call it? Yeah, here it's just x1 xn times y1 yn. This is x1 y1 x2 y2 xn y1 yn. Is it clear?
Yeah. Thank you.
Yeah.
Okay, any more questions, comments?
Yeah, here.
I have another question. So you told about analogy between classical mechanics and quantum mechanics.
Yes.
So you write the Poisson algebra analogy equivalent Hopf algebra. So is it a simple analogy or a one-to-one map?
In fact, I talked about two separate things, two different things. The first point is just to illustrate the fact that that a quantum mechanic is a deformation of classical mechanics. Of course, I have to go deeply and say we are considering also groups. Huh? We have to see that Lorentz group is somehow a deformation of a Galilei group. But what was suggested by this Buffels group, I mentioned here, is that we say that we call this quantization deformation. This is called quantization deformation. Quantization deformation. And to get the quantization deformation, we have to deform the product, this Poisson algebra, in order to get a non-commutative algebra, still associative, of course. And this was done, for example, for symplectic manifolds and completed by Kontsevich, who showed how to construct, given any Poisson algebra, you can construct a star product, which means a deformation using some graphs, etc. This is one thing, and I talked about this Hopf algebra. This Hopf algebra is a sort of generalization of the concept of groups. That's why I put here this group concept, and I should say that this Hopf algebra structure is a sort of generalization of group concept. That's why some of the examples are called quantum groups. Of course, they are not a group. They are Hopf algebra, which means that you have two operations. You have a multiplication, a co-multiplication, a unit and co-unit, and an antipode. This is the all ingredient which give this Hopf algebra structure. And when you do that for enveloping algebra, which is an associative algebra associated to a Lie algebra, we may talk about that next lecture, my next lecture, and then we have this deformations of the classical algebra structure of an enveloping algebra. We have very easy Hopf algebra structure on any enveloping algebra, and our objective is to deform this. When you deform that, you get what we call a quantum group. And they said that this is related to quantum inverse. Now I have a complete name. This is a quantum inverse scattering method. Quantum inverse scattering method. And this is a method to deal with integrable systems. With, of course, quantum integrable systems. Then this is two different things, which motivates somehow the study of deformation. Is it clear?
It's okay. Thank you.
Welcome.
Okay, let's thank the speaker again.